Thank you all. So I'm going to give you an overview and update on Array, which is a distributed execution engine for Python. And to start off, let's look at the machine learning landscape today. So many people think of model training if they hear machine learning, but of course the problem is much broader. Before you can train your model, you need to featureize your data, and then after you train the model, maybe you do some hyperparameter tuning as part of the model training. You need to serve the model to users, potentially execute it on streaming data. And actually there's applications, for example, online learning and reinforcement learning, where many of these are integrated in a very tight loop. For example, for reinforcement learning, you have to do simulation, training, and model serving in a tight loop. And for online learning, you have to do featureization, training, and model serving. So these applications are also very compute intensive, so they need to be run distributed. And the way that people do this nowadays is they use different distributed systems for each of these boxes. So for example, for featureization, they might use a system like Spark. For training, they might use a system like distributed TensorFlow. And for model serving, they might use a system like Clipper. So this comes with overheads, both for developers, because they need to learn different APIs, different systems, potentially different programming languages. And then also for the runtime, because there's inefficiencies in terms of data transfer between systems, and the fault tolerance between the systems need to be reconciliated. And then also in terms of the operations, it's expensive because different systems have to be managed. So instead, we propose to go to this picture, where we can share a common framework amongst these workloads. And this is Ray. So Ray encapsulates all the hard problems of distributed computing, things like memory management, scheduling, talking between machines, fault tolerance, and so on. And then on top of that, we can build libraries for these different machine learning applications. And you will hear throughout the day about various libraries that have already been built. So Devin is going to talk about data processing library. Richard is going to talk about hyperparameter tuning and training. And Eric is going to talk about reinforcement learning. Okay, so now let's look at one motivating example, which is online learning. So this is actually a system that was built at Ant Financial. And they have an online learning system where, based on some user features, they recommend different products to the user. And so this encompasses featureizing the data, training a model, and then doing serving in a loop. And the system they started off with used different systems for each of these parts. And it took about, the whole loop took about 1 day. So they collected data throughout the day and then trained a model and served it. And then the natural question is, if you speed this up, how much benefit can you get? And so first, they really engineered more about the system and brought this down from 1 day to 1 hour. And this led to an increase of the click-through rate by 5%. And then, of course, the question is, how far can you go? So the 1 hour solution was already using state-of-the-art solutions for each of these pieces. So they ported the system on top of Ray, and then could get the online learning loop down to 5 minutes. And this gave another 1% in click-through rate. Okay, let me now walk you through how the system works. So first we will start off with a serial Python program. So we have a function f, which takes some input x, then does some computation. Think about some expensive computation like evaluating neural network, and then it returns the result. If we execute this, we first start with calling f of a, assign this to a variable x, and then the interpreter will execute this, and it takes maybe 1 second to execute the function. And then the second line gets executed, which evaluates f on b, and assigns the value to y. And this again takes 1 second. So the overall computation took 2 seconds. Now with Ray, we can parallelize this. And there's one process, which is the driver process, that submits the computation. So we changed the function to be a remote function by putting the ray.remote decorator in front of the function. And then in order to call the function, we call f.remote. So let's go through how the execution is going to proceed. So first, the first f.remote on A is being called, and then it will be scheduled on a worker, and this will happen instantly, and the driver process is going to return. And then, immediately afterwards, the second line is executing, which calls f.remote on B. And again, this is instant. And then the driver is going to call ray.get on the results. So the results here are, if you're familiar with futures, these are sort of representations of the result. And you can call ray.get to get the actual value corresponding to them. So now the worker starts executing, and on each worker it takes 1 second to execute the function. And then after 1 second, the function returns, and then we have the 2 results on each of the workers. And then Ray ships the result to the driver, and now we have the results of X and Y on the driver. So this was a very simple parallelization of a, for example, data processing application. So this is about half of the Ray API, and this is tasks. So tasks are stateless functions distributed. But oftentimes, machine learning applications are stateful. So for example, for reinforcement learning, we need to keep the state of simulators around. For machine learning training, we need to keep the state of parameters in a parameter server, and so on. So for this, we introduce Ray actors. And these are Python classes that are decorated with the ray.remote decorator. So let me illustrate this with a simple example. This is a simple counter class, which gets initialized with 0. And then you can increase the counter or get the value. And then in order to call this, we first instantiate the class with counter.remote. And then we can call the method with actor.methodName.remote. OK, so let's walk through how the execution is going to proceed. So first, the remote actor is going to be created with counter.remote. And that will spin up a new process and instantiate the class. So in the process, the constructor will get run, and the value is going to be equal to 0. So while this is happening, the driver already proceeds to the next step and submits the increase function. And then this will be queued up in the actor. Because the actor is currently not processing anything, it can be moved from the queue, and the actor can start executing. So it will run the self.value plus equal to 1 line. While this is executing, the driver will submit the next function, which is the increase function, again. And then the initial increase function is going to terminate, and so now the value is equal to 1. While this is happening, the driver is also going to submit the c.value.remote function, which is going to be queued up in the actor. And then the actor grabs the next method from the queue, which is increase, executes it, and so after execution, the value now is equal to 2. The driver, in the meantime, calls ray.get on the value. So the actor starts executing the value function, gets the current value, which is 2, and then returns it to the driver, and then the ray.get can return, and we get the result.
Question.
Yeah.
System calls to increment, are they asynchronous?
So these two will run, the one on the driver are asynchronous, so they will immediately be submitted to the actor, and then they will run in sequence on the actor. That's right. So the state is well defined at each state of the execution. And in order to get parallelism, you start multiple actors and execute multiple things in parallel. So these two paradigms, tasks and actors that I just showed, can also be very easily combined. So you can, for example, pass actors to tasks. You can pass any of the objects that were created by actors or tasks into either actors or tasks. One example on how this could be used, for example, is to write a parameter server where you have some worker task that gets the latest parameter, updates it, computes the gradients, and then submits the new parameter to the parameter server. And in order to shard the parameter server, for example, you could just run multiple actors in parallel. OK, so this was the array execution model, and in fact, you will go over this yourself in the tutorial. So let me now give you some updates about Ray. So one new feature is now memory limits. So this solves a problem that was frequently occurring when you had a very intensive workload. Oftentimes, if one process, for example, was generating too much data, then things could slow down. And so now you can specify memory limits on actors, both on the actual process and then also on the amount of memory that they can share with other actors. And yeah. So the memory parameter is local memory of the actor, and the object store is the shared memory, and you can limit both of them. So shared memory is on each node, there's a shared memory object store, and this is in RAM. So yeah, it's not persistent, it's in RAM.
So is that an allocation, or is that a limit that will shut down gracefully if it exceeds? Or is it allocated?
So it's a limit, and what this does is it gives you the right error messages if things go wrong. And also it makes it so that the shared memory is actually, it makes it so that the actor will not use more than that amount of shared memory. The second feature is array projects. So array projects makes it very easy for you to package up your application. So to put this in context, for distributed applications, it's often hard to bundle all the dependencies. So typically, you need more than the source code to run the application. In fact, you need cluster configurations, you need libraries, you need input data, you need machine learning models, and things like that. And so array projects are, we have a simple description language, a YAML file that configures the array project, and then it makes it very easy for you to run these projects on a cluster and also share them with other people. One change that is a bit more internal is we've been working on a common worker implementation for Python and Java. So how it used to work is here on the left side, and we had the Raylet, which is in C++, and then the different worker processes have libraries. So there's a Python library and a Java library for these. But there was a lot of functionality that was shared between the two. And so we factored this out into a common C++ worker, and this allows us to both make it easier to build language front ends and also to speed up the execution. And then a few more changes. So there was a lot of work on the documentation, so you should check that out. And then there's some ongoing improvements that we are working on, which is improvements on the serialization side to make it possible to support more different data types at the same fast speed that we have at the moment. And then also to improve Ray's garbage collection even further. Okay, so since the last RISE camp, we had a lot of growing adoption. So we now have 205 contributors, which is more than 2x the amount that we had at the last camp. And then we have now 9K stars, which is also more than 2x what we had at the last RISE camp. And we are running tutorials at O'Reilly. In fact, just this week, we ran a tutorial in London, which was attended by over 90 people. And then Ray is also now a part of AWS SageMaker. And there's a continuing and increasing number of use cases, production use cases at companies. Also in terms of documentation views, they increased from about 4.3K to over 10K. And then the number of downloads since 2018. So this is from the beginning of 2019 up to date. Is more than 4.5x the amount that we had last year. So that's very exciting to see. Also, we are organizing a meetup in San Francisco, which will be next Wednesday, October the 23rd. And there are still some open spots, so if you would like to join, please let us know. There will also be a link on the survey where you can sign up. Okay, we will now go through a tutorial, which will cover both Ray actors and tasks, and then also some more advanced material. And in order to run the tutorial, the easiest way is probably if you just, there's a little piece of paper that you got, and so you go to the URL. So this is rise.camp. And then you put in the password on the paper. And after you do this, you get to this page, where the first part is the Ray tutorial, and then you click on the link, remote functions. So this will open up a notebook in Google Colab. So you can do either of two things. You can either say that you want to authorize this. Or you could also say you want to save a copy in Drive. And then you will have a local copy of this. So has everybody succeeded in going to the tutorial and bringing up this notebook? And there's also people.
What do they do to initialize install dependencies? You went too fast and I looked away.
Sorry, Seiko.
Install dependencies, what do I do?
Oh yeah, install dependencies, you just run the cell. So I'll actually walk you through it. There's a bunch of dependencies that we need. So the first cell just installs these dependencies, and then it restarts the runtime with ox.exit. So you just run this cell, for example, by clicking this button. Please raise your hand if you don't succeed in going to this page. Okay, so it takes a little bit of time to install. And then it will restart the runtime. You don't actually need to click this button, it does it automatically. Okay, and we can ignore this. Okay, so now the first part is doing a very simple parallelization.
I'm sorry to interrupt with an announcement. If anybody owns red Tesla and parked it in the International House parking lot, it's about to get towed, so please move it.
Okay, so did it succeed installing for everybody? Okay, let me. That's right. Let me come to you. Okay. So if you got a little error message down here that said crashed, that's actually not crashing. So that's this os.exit call here in order to restart the runtime so it uses the new libraries. You can just close it. Yeah. Please raise your hand if you get stuck, and then somebody will come to you and help you. Okay, so in each exercise, it gives you a description on what you're supposed to do for this exercise. So in the first exercise, we go through how to parallelize a simple function. And so down here is the first cell. So you can execute that cell. And this will first import array and some other library. And then in the second cell, we call array.init. So this initializes array and brings up all the array processes. So then, after this has proceeded, we want to parallelize this function. So let's first see what happens if we run this function without parallelizing it. So we can run the cell without modifying it. And this will do some computation. So it calls a simple sleep function 4 times. Oh, yeah. Maybe that's a bit too big. Okay, so there's this slow function which sleeps for 1 second and then returns an integer. And in this case, we just run it 4 times and append the results to a list, and then we print the time. So it took 4 seconds because they were executed in serial. Then there's these cells that test if the exercise has been done correctly. And so let's run the cell. And it prints an assertion error. So it tells us the loop took 4 seconds. This is too slow. So now we have to do the exercise and speed it up. So to do this, we just follow the instructions that are up here. And I'll just show you. So Oh, did everybody get to this point so far? If you don't, please raise your hands. And keep them up, and then somebody will come to you. Yeah, so this is actually using Google Colab, which is a hosted notebook which runs on the cloud, and it gives you like a small machine with, I think, 4 cores and like a few gigabytes of memory. You can also run this locally. I can actually, yeah, I mean, for the tutorial, it's best to run it with Google Colab. So, I mean, this runs on some like cloud infrastructure. I'm not sure, probably inside of some Docker container or something like this. I mean, this is hosted by Google, actually. So, I mean, if you run it yourself, then you are very free. You can run it on AWS, you can run it on Kubernetes, you can run it on your own infrastructure. We actually have this part of Array called the autoscaler, and it makes it very easy for you to bring up a cluster either on the cloud or inside of your own environment, and then making it possible to scale the cluster dynamically up and down. So, and if you want to learn about these things, you can look at the Array documentation. So, there's different companies that run different setups. Some of them are running Kubernetes, some of them run it on the cloud. This particular one is just using the hosted Google infrastructure, just for this tutorial.
I'm sorry, can you go up to your import statements and describe them at all? So there. So
Yeah.
From future import, are those Ray specific, or is that something that I might have encountered if I?
So this is Python. So this means, yeah, this makes it possible to be compatible with both Python 2 and Python 3. There are some differences in behavior between Python 2 and Python 3, and if you write down these import commands, it will bring some of the Python 3 behavior to Python 2, in case you're running Python 2. It's actually very useful, probably on top of, so in Ray, on top of each of the files, we actually put these statements.
So let's say when you start the array, how do you figure out what is the memory limits that you need to apply? Is it based on the underlying host and the resources available on the host?
Sorry, can you repeat the question?
So at the very first cell, when you initialize the array,
Yeah.
it says starting array with 6.3 GB memory and things. So where are these limits calculated? Are they calculated based on the host resources like memory and virtual cores?
Right, so the question is, here it shows starting array with 6 gigabytes of memory and 3 gigabytes for objects. So it depends. If you run it on your laptop, for example, then you just call array.init with no further arguments, and then it will just use all the resources of your laptop. So for example, the number of cores and the memory. This is for single machines. If you run it on a cluster, then you typically set up the cluster in some way, for example, with the autoscaler, and then in the array.init, you specify an address to connect to the cluster, and then it will just use all the resources on the cluster. And you can actually configure, when you start it up, how many cores and how much memory you want to use. Okay, so now let's continue with the tutorial, and let's put the array.remote decorator in front of the function. And then we also need to call, instead of slow function, we call slow function.remote. So this will make it so that the function gets submitted immediately, and then the for loop can proceed to the next function. And so then all the functions run in parallel in the background. And then at the end, so now the results, instead of being concrete values, they are these array futures, which are object IDs. And now we have to call array.get. So we say results equals to array.get of results. So just let's just have a quick look at what would happen if we would omit this. If I don't put this, then the results would be these object IDs instead of being concrete values. So let's put the statement back. And now we get the same printout as before. Okay, and now we can run the next cell to check. And now it says success example took 1 second, a bit more than 1 second. So this means that it has now been parallelized using array. So please raise your hand if you couldn't. So what I did is I put ray.remote in front of the function. And then I call function name.remote. And then I call ray.get on the result.
Excuse me.
Yeah.
Could you show the Chrome tracing part once?
Sorry, show.
The Chrome tracing section, which is right above, before parallelizing.
Oh, the code before?
Yeah, the Chrome tracing where you export the ray timeline and view it in Chrome tracing window.
Oh, the next, yeah. You're asking about the next question, or?
Yes, before exercise 2, the cell before exercise 2.
Oh, yeah. So that's the next step.
Oh, that's
So in order to visualize what is going on in the cluster, we have the timeline. So there's the ray.timeline command, which takes a file name, and then it will export all the information on when each task was running. So let's run the cell. And what it will do, it will produce this exercise1.json file. So in order to see this, you go on the left-hand side, you go to the Files tab, and then you can download this file by, let's see, right-clicking and then clicking the download button. So then you have the file locally on your laptop, and in order to visualize it, you open this Chrome timeline. So this unfortunately only works in Google Chrome. So you say Chrome : // and then you can press enter. So this will bring you to this tracing view, and there you can press the load button, and then you navigate to the download to the file, and then you click open. And then it will open the timeline, and it will show you. So there was a bunch of waiting period because it took me a while to start the exercise, and then we have the tasks that are executed. And you can actually zoom in by using this little tool here, and then pressing down and up. And so this allows you to see which tasks have been executed. Okay, so let me say this again. So you execute this ray.timeline button, and then you go to the Files tab. You download the JSON file, and then you go to the Chrome tracing and click the load button and load the JSON file that you just saved. Okay. So yeah, for the rest of the tutorial, we will actually, you can go through these at your own pace, and we will just go around and help you.